we shall start our discussion on Rankine cycle, and in today's class we will try to see the advantageous feature of the Rankine cycle in the context of vapor power cycle, and finally we will try to discuss about the irreversibility associated with this cycle. So, I mean if we try to recall, in the last class we have talked about the Carnot cycle, that is the ideal cycle. In fact, this is one of the important ideal cycles which is used for, I mean which you need to study. In fact, we have studied in our thermodynamics course, and from the discussion of the Carnot cycle we have listed down a few serious drawbacks if we try to run the steam power plant using the Carnot cycle. What are the problems or drawbacks of the Carnot vapor cycle? That means, if we try to run the vapor cycle using the Carnot or ideal cycle, we have seen there are 4 important drawbacks. One is the partial condensation. So, before coming to the Rankine cycle, let us briefly recapitulate those aspects. So, one is, so I am writing Carnot cycle drawbacks. First is partial condensation. Okay. In fact, let us first draw the TS diagram, and from there we try to, if I try to draw using different color, say I am drawing using this color. Okay. And so this is TL, this is TH. Okay. If I give the name, so this is 1, 2, 3, 4, and in the right hand side what we can do, we can try to have the schematic depiction of the steam power plant. So, this is boiler, say this is compressor, we have turbine, and from we have one condenser. Okay. So, this is a the processes which are there to, and processes constitute this cycle. I mean we have identified in the last class. So, there is heat addition Q in, this is work input, this is heat rejection Q out, and this is work output W out. So, this is 1, this is 2, this is 3, this is 4. Now, 1 to 2, process 1 to 2, so process 1 to 2, let me, I have done mistake in giving the identifying the points over here. So, let me write it. So, 1 to 2, that is, so this is 1, this is 2, this is 3, this is 4. Okay. So, we have discussed in detail about this cycle. Now, today for the recapitulation I would like to discuss about the drawbacks. First of all, you try to understand this is a compressor. So, the collected condensate will be compressed and it will be taken to the boiler to complete the cycle. Since we can understand the process 4 to 1, that is the condensation process, right. Now, what we can see from the TS diagram is that the point 1, that is the condensation process, is getting terminated at point 1 and that is still 2 phase mixture. So, it is not so easy to have a control on the condensation process as it is partial condensation, right. It is not the case that the condensation process is extended up to the saturated liquid line, right. So, this is the saturated liquid line and this is the saturated vapor line, and this is saturated liquid line, and this is the critical point. These two lines meet together and that is the critical point. Those we have studied in our thermodynamics course. So, first drawback is that the partial condensation is very difficult. So, we need to design the condenser in such a way, and we also need to have a control on the condensation process itself, so that the condensation process will terminate at point 1, number 1. So, that is partial condensation. Number 2 is work ratio, probably you have seen. So, what is the work ratio? Work ratio is basically the net work by the input work, right, that you have studied, that we have discussed in the last class. So, the work ratio, that is the net work by the positive work. See, if we need to compress this 2 phase mixture, we can see the process 1 to 2, that is the compression process. So, basically we need to compress the 2 phase mixture and eventually it will be terminated at point 2, that is saturated liquid. So, to design a compressor which will compress a 2 phase liquid, 2 phase mixture, and at the end of the compression process we will be getting saturated liquid. So, again it is very difficult task to have a compressor which will perform the process like this. Not only that, as I told you, work ratio, that is net work by the positive work. So, positive work from the cycle is the work output from the turbine. Our entire objective to get work output from the turbine, because this turbine shaft that I have drawn over here will be connected to the shaft of an alternator, and from there we will be getting electricity. Question is, our objective, since our objective is to maximize the work output, but out of this positive work we are also having some work input to the system. So, when we will try to analyze the cycle, we will see that this work will be supplied to the compressor and we are getting work output from the turbine. So, what is the fraction of the positive work output, that we need to measure. Since compressor will be handling 2 phase mixture and you know that the specific volume of vapor is very high, then the work input to the compressor will be very high. Since again I am telling, since compressor will be handling 2 phase mixture, I am not even going to the design aspect of the compressor. So, there are 2 difficulties. First of all, it will handle 2 phase mixture and the compressor eventually will be designed in such a way that at the end of the compression we will be getting saturated liquid, if we need to run the vapor power cycle following the Carnot cycle, that is the ideal cycle. So, that is the difficulty from the perspective of the design aspect of the compressor. Number 2 is that compressor will be handling 2 phase mixture, since the specific volume of vapor is very high as compared to the specific volume of liquid. Had it been, if the quality or thermodynamic state at point 1 had it been completely liquid, then probably we could have needed relatively lesser work input to the process. So, since at state point 1 substantial amount is, I can say, from you can see from this TS plane that vapor. So, to compress vapor we need to supply more work input. Since we need to supply more work input, that will reduce the work output, work ratio. So, that is called compression work. which is very high. Number 3, which is again important, if you look at the TS diagram, that we can see from that is that steam quality at the exit. See, steam quality at the exit. So, basically 3 to 4 the process which occurs inside the turbine, that is nothing but from the TS plane entropy is remaining constant from 3 to 4. So, I mean we really do not know, but still it is reversible adiabatic process. So, turbine walls are insulated. So, there is no heat loss from the turbine wall to the surroundings, because at the inlet to the turbine the steam which is entering is having high enthalpy, and when steam is expanding it does work on the rotating part of the turbine, and from there we are getting work output. Since if we allow heat to transfer from the while steam is expanding inside the turbine, and during the process of expansion if we allow heat to transfer from turbine to the surroundings, then we will be getting less work output. So, that is why this is adiabatic process, and we can see the process is internally reversible. So, this is reversible adiabatic process which is nothing but isentropic process, and that is why you can see entropy at 0.3 and entropy at 0.4, these two entropies are equal. Now, what we can see from the TS plane, that at 0.4 what is the quality? It is again two phase mixture. Not only that, since it is slightly, not slightly, it is away from the saturated vapor line, I mean more this point is away from the saturated vapor line, more it is having moisture content, and this will lead to the turbine blade erosion problem and pitting. So, I am writing that quality of steam at 0.4 is poor. Okay. So, steam quality at the exit is poor. So, I mean having discussion on these drawbacks, next we should move to discuss about the ideal Rankine cycle. See, this is the ideal Rankine cycle that was proposed by a Scottish mathematician, which is William John Rankine. So, the ideal Rankine cycle was first proposed by a Scottish mathematician William John Rankine. So, now question is, if we go back to the previous slide, we have discussed about the partial condensation. So, partial condensation, I mean it is problematic from two different perspectives. First of all, designing a compressor which will compress saturate two phase mixture, and at the end of the compression process it will deliver saturated liquid. So, it is not so easy. On the top of that, compressing two phase mixture it is a power consuming process. So, we need to supply high work input to the compressor for its operation. So, in the Rankine cycle, that Scottish mathematician proposed that instead of compressor, if we put a pump, if the compressor is replaced by a pump, then perhaps, so let me draw the schematic again. So, this is boiler, so this is pump, and this is turbine, so this is condenser. So, this is 0.1, this is 0.2, this is 0.3, this is 0.4. Again this is a cyclic process, we are having heat input, work output, this is turbine, this is condenser, this is heat rejection and this is work input to the pump. We will try to draw the TS diagram again. Okay. So, say now let me discuss about this particular cycle. If we compare this schematic with the schematic that I have drawn over here, you can see everything is remaining same except the compressor part. So, here again it is insulated, no heat loss from the turbine to the surroundings. So, here we are having pump, you know that pump can handle liquid, since pump cannot handle two phase mixture. So, if we replace compressor by a pump, we have to have the liquid state at point 1 is the liquid. Okay. So, while condensation process was the partial condensation, that is it is getting terminated at point 1. Now, since pump cannot handle two phase mixture, this condensation should be extended up to the saturated liquid line. So, if we try to draw the process line, that is the condensation process, say this is point 1, right. Then 1 to 2, that is pumping process we have seen. So, 1 to 2 I am writing process 1 to 2. Process 1 to 2, that is reversible adiabatic process, right. See, while liquid is pumped from state 1 to state point 2 up to the boiler pressure, so there is no heat interaction. So, pump is again a device which is work interacting device. By taking work as input, it can pump liquid from state point 1 to state point 2 to the boiler pressure. So, from the condenser pressure to the boiler pressure. So, say this is point 2 and it is pumping. So, this is point 2. So, this is point 2, right, and then 2 to boiler is operated at constant pressure. So, when liquid is taken to the boiler, boiler is a heat interacting device. It will, in boiler, water will be converted into steam upon receiving heat from the external source, right. So, if it is coal fired boiler, so then in most of the thermal power plant, if it is boilers are coal fired boiler. So, the amount of heat that will be supplied to the boiler will come from burning coal. There are diesel fired boilers, but in the coal fired boiler, so heat will come from external source and which will come from burning of the coal, and the process which is a constant pressure process. So, water will be converted into steam following the constant pressure process. So, in the TS line, if we try to draw the constant pressure line, so it will be like this. Say this is okay. So, this is point 2, this is point 1, and so this process ends at point 3. Our objective should be to, so this is point 3. Our objective should be to get steam which is coming out from the boiler before it enters into the turbine will be in a saturated vapor state. So, moisture content will be 0. If the steam that we are getting from the boiler at the inlet to the turbine is having moisture content, so that will lead to the turbine blade erosion. So, it will not a good design to have the process, the constant pressure heat addition process. So, inside the boiler we are having constant pressure heat addition process, and following that process water will be converted into the steam, and then from 3 to 4 we will be having. So, this is 0.4. So, this is 3 4. So, this is 3 to 4, that is the expansion of the steam. As it moves in the, as steam moves from inlet to the outlet of the turbine, it does work as I said you on the rotating part of the turbine, and it enthalpy drops. Since enthalpy drops, temperature also will be reduced, and that we can see, and that we are getting at 0.4. So, it is isentropic compression process. So, process 1 to 2 is reversible adiabatic process, process 2 to 3 is constant pressure heat addition process. Four to 3 to 4, that is reversible adiabatic expansion process. And 4 to 1, that is constant pressure heat rejection. So, all these 4 processes we have identified. So, and all these 4 processes constitute the cycle that we are talking about. So, try to understand that if we now try to compare the this ideal Rankine cycle. Why we are calling ideal Rankine cycle? Because let me tell you something here. If we know that the Carnot cycle is the ideal cycle, and you have studied that ideal things, whether it is ideal fluid, ideal gas, ideal process, this ideal. So, this idealism. So, basically it is very difficult to implement those ideal things in reality, but having a proper understanding about the implementation difficulties of the ideal things, ideal stuffs in reality, why do we need to study these ideal, rather we need to understand about these ideal processes. Question is, let me tell you that we always need. So, basically if we we know that whatever we can see in reality, those are the actual things, but when we are trying to improve the, since in actual processes, actual things, there will be losses, right. So, the actual process can never meet the ideal processes, but our intention should be to improve the actual processes, actual systems, actual things, to bring them closer to the ideal ones. So, if we need to have the, it is very difficult to meet the ideal processes, but our intention should be to bring them closer to the ideal processes, and that is why we should have a proper understanding about the ideal processes. Similarly, in this particular topics also, though we know the Carnot cycle is very difficult to implement, difficult to achieve in practice, even then we are studying this, we are studying about this particular cycle only to know that when we will be talking about the actual or real cycles, at least efforts should be taken to bring those actual cycles closer to the ideal one. If we need to bring them closer to the ideal ones, what are the modification, what are the design steps, we should, what are the modifications needed to design or to make the actual cycles closer to the ideal one should be clear. So, So, from that is why we are studying actual ideal cycle. But now if we compare this ideal this ideal Rankine cycle with the ideal Carnot cycle, why we are calling ideal Rankine cycle? We are considering all the processes are internally reversible, though it is very difficult to achieve. I mean, if you need to have a process to be internally reversible, so the process should be quasi static process, right, that we have studied in classical thermodynamics. If we need to have the process to be quasi static process essentially to achieve the internally reversibility, then I mean we have seen that a process, if it is said to be quasi static process, so infinite slowness is the characteristic feature of the quasi static process. So, process will be very, very slow. Even then, at least we can bring this Rankine cycle, and we are calling this ideal cycle ideal Rankine cycle, so that efficiency of the Rankine cycle which is very, very close to the ideal Carnot cycle, and that is why it is called ideal Rankine cycle. So, we will try to discuss the ideal Rankine cycle now. Why it is calling ideal Rankine cycle? Because efficiency of this Rankine cycle is very, very closer to the Carnot cycle, and that is why it is called ideal Rankine cycle. But okay, now see why it is very, very closer to the ideal Carnot cycle. Why not is why the efficiency of Rankine cycle is not equal to that of the Carnot cycle? Try to understand one important thing. See, efficiency of the ideal Rankine cycle, ideal Carnot cycle is 1 minus TL by TH, that you have studied in thermodynamics course. So, this TL is the temperature of heat rejection, and this is temperature at which heat is added to the system, right. You can see the temperature at which heat is added, which is takes place, I mean here the process 2 to 3 which is taking place inside the boiler. So, again this is ideal cycle, we can just to have, I mean we can conceptualize this cycle, but it is very difficult to mimic this cycle in reality, in practice. Okay. So, you can see that the heating process, that is sensible heating. So, sensible heating is always efficiency of the sensible heating is always higher than the efficiency of the latent heating. I mean so this is latent heating, right. Phase change heat transfer theory, I am sorry, by I have said by mistake this is sensible heat transfer. So, process 2 to 3 in which heat transfer takes place, that is the phase change heat transfer, right, and phase change heat transfer is always efficient, rather it is much more efficient than the latent heat transfer, sensible heat transfer. So, the phase change heat transfer is always efficient than the sensible heat transfer. So, in the Carnot cycle process 2 to 3, that is the phase change heat transfer. But if we now go to the ideal Rankine cycle, there is a part, say it is 2 prime. So, 2 to 2 prime, that heat transfer, that is the sensible heat transfer, while 2 prime to 3, that is the phase change heat transfer. So, because of this component of heat transfer, the average temperature, because now you can say that heat addition is TH. So, the presence of this component of heat transfer will reduce the temperature at which heat is added to the system, right. So, if we try to write the efficiency of the ideal Rankine cycle now, so equal to 1 minus TL by TH. I should not write TH over here. See, it is not, TL is fine. So, this is that heat is rejected in this condenser during this condensation process. Now, this TH is not TH. So, this is TH mean. Why this is mean? Because a part of the heat addition process is this is heat addition at that is a sensible heat addition, right. So, because of this sensible heat addition component, mean temperature of heat addition reduces, as a result of which if it get if the mean temperature at which it is rejected, heat is added to the system. So, the mean temperature at which heat is added to the system is less than the temperature at which it is added to the system for the ideal Carnot cycle, then you can understand the ideal Rankine cycle efficiency will be definitely lesser than the efficiency of the ideal Carnot cycle. Okay. So, which is responsible because the component this latent heat addition component will reduce the average temperature at which heat is added to the system, which in turn will reduce the efficiency of the ideal Rankine cycle. Okay. So, though we are talking about that all the processes are internally reversible, we are trying to bring the efficiency of the this Rankine cycle closer to the efficiency of the ideal Carnot cycle, and that is why we are trying to give the name ideal Rankine cycle. Yet because of this fellow, that the latent heat sensible heat addition component, average temperature at which heat is added will reduce, which in turn will reduce the efficiency of the Rankine cycle. Okay. But the problem is, now the problem which we had the condensation process, that problem is not there. We can design a condenser which will now have condensation up to the saturated liquid line. So, the problem associated with the partial condensation is no more. Second thing is, instead of a pump, instead of a compressor, as the case is following this ideal Carnot cycle, we are now having pump. Since the condensation process terminates at point 4, which is saturated liquid, pump can easily handle that liquid, and while we are having pump, it is only handling saturated liquid. So, the work consumption, the power consumption, work input to the pump is significantly less than the work which was added to the compressor for the equal power output. For the same power output, the work added to compressor only to handle substantial amount of vapor which is having high specific volume, the work input, the required work input to the pump is less, as a result of which the work ratio for the turbine for following this ideal Rankine cycle will be very high. So, the problem associated with this partial condensation, problem associated with the high work input of compressing two phase mixture, as was the case in case of a ideal Rankine cycle, is not here. But you can see the process 3 to 4 is again reversible adiabatic expansion process. All these processes are reversible process, internally reversible, and that is why you can say it ideal Rankine cycle. But you can see this expansion process even terminates at point 4, which is even away from the saturated vapor line. So, at point 4 still the quality of the steam is not very good. So, the moisture content will, so basically towards the end of the expansion process, the quality of the steam will reduce, which in turn will lead to the turbine blade erosion problem. So, I mean we need to think about the modification of the simple Rankine cycle such that the problem associated with the high moisture content or moisture content of the steam at the outlet of the turbine can be eliminated. But so far we have understood that the problem associated with the partial condensation process and also the high work input required for compressing two phase mixture for the case when we have discussed about the ideal Carnot cycle, these problems are not there in case of the ideal Rankine cycle. But still the problem of this moisture content of the steam at the exit of the turbine is there, but we can think of the modification of the Carnot modification of the ideal Rankine cycle. We shall discuss those aspects again, but for the time being let us now discuss about if we I mean this is what we have discussed till now, but since we are engineer we will try to quantify the efficiency of the, see if we have a thermal power plant, and if the thermal power plant is designed to run following the ideal Rankine cycle, what would be the efficiency for the given heat input, right. So, we shall now try to estimate, rather we shall try to do the analysis of different processes which we have listed down over here, and then we shall try to quantify the efficiency, thermal efficiency of the ideal Rankine cycle. Okay. So, before that, I mean it is very difficult, it is very, I mean it would be convenient to understand if we discuss one important thing. So, all the processes which are there, I mean all 4 processes constitute this cycle, right. So, process 2 to 3, constant pressure heat addition process, internally reversible. We are assuming 3 to 4, that is again isentropic expansion process, that is reversible adiabatic expansion, internally reversible. Process 4 to 1, constant pressure heat reduction, again we are assuming this is internally reversible. Process 1 to 2, that is reversible adiabatic pumping, reversible adiabatic process, right. All these 4 processes, if we need to analyze all these 4 processes, essentially to quantify the efficiency of the power plant, which if we consider is being, or which if we consider is operated based on this ideal Rankine cycle, we have to consider all the processes are steady flow, steady state, steady flow processes. So, if we consider steady state, steady flow processes, probably you have heard about this. So, you can understand steady state, steady flow processes, in short it is called SSSF processes. Okay. So, now we have studied about first law of thermodynamics, second law of thermodynamics. So, if we apply first law, if we consider all the processes are steady state, steady flow processes, and if we apply first law applied to steady state, steady flow processes, what are those processes? Constant pressure heat addition, isentropic expansion, constant pressure heat rejection, and reversible adiabatic pumping. So, let me write the first law applied to flow processes. So, first law applied to flow processes. Processes are steady state, steady flow. First law applied to flow processes, to be precise steady state, steady flow processes. We can write cube dot plus, you have studied this in thermodynamics course, I am not going to derive this equation, but just I am writing right. In this equation try to understand. So, this is the generic equation I have written. As I told you that I am not going to derive this equation, this is not included in the content of this course. Also, so this is energy balance equation. So, this is energy balance equation, together with the mass conservation we can write summation of m dot I equal to summation of m dot E, because dm CVDT is equal to 0. So, there is no net change of net rate of change of mass inside the control volume. So, this is flow processes. So, we are applying the equations to a control volume. So, now we have written this equation, that is Q dot, Mi dot, W dot. So, this is a rate equation. So, this is rate equation. But if I want, we can just remove dot and we can write the general form of the equation, but Say we are not interested to write the equation in the rate form. So, what we can write? We can write, and we are having single inlet, and so this is m dot e. If we have single entry, single exit, so we can write m I equal to m e equal to m for single entry and single exit. See, it is quite obvious. So, now if liquid enters to the boiler through a, I mean you are having one or single inlet and steam is coming out from the boiler single outlet. Similarly, for the turbine and condenser and pump also. So, pump liquid enters to the pump through a single inlet and it comes out from the pump through the single outlet. So, that is m dot I equal to m dot e equal to m, that is single entry, single exit. Okay. So, and if we have this, and if you do not want to write the equation in the rate form, rather in the much normal form, then we can write q equal q plus m. Say we are having process. So, if we have process inlet and process outlet, so I am writing h I square plus v I square by 2 plus g z I equal to w plus m h e plus v square by 2 plus z e. Okay. So, let me write it, right. We can also write one step further. What we can do? We can write, we can take this m and we can write this in the specific form. So, I can write cube and small w. Understood? So, we are writing specific heat transfer in the specific quantities. Okay. So, this part you have studied in thermodynamics, I am not going to read. Now, just we have listed down this important equation, this and this, just I am these two equations. We will be applying these two equations. I mean we have already, so first equation, that is m dot I equal to m, I equal to m is equal to m, that we have already taken care in the final equation. So, if we apply the last equation to all the flow processes, so if I apply, so now if I apply for the boiler, so process 2 to 3, see here process 2 to 3, that is constant pressure heat addition process. Control volume is not doing any work, flow work is there. Try to understand, again I am discussing little bit about thermodynamics that you have studied, I guess. In most of the textbooks, I mean they are writing in a different form, in different form, but try to understand in the boiler, that is constant pressure heat addition, right. In this constant pressure heat addition, we are applying first law applied to the flow process, and we are going, if we consider a control volume, that control volume is not doing any work, but the flow work is there. So, that is there is a steady flow always. To maintain the flow in presence of pressure, we need to do flow work. So, now, so this is this boiler is not a work interacting device, to be precise. Since it is a heat interacting device, if we apply this law, so this W will be equal to 0, and I can write Q, and if we consider the changes in kinetic and potential energy is negligible. So, if we consider changes in kinetic energy and potential energy are negligible, then what we can write? We can write Q 1 to 2, say I mean I am writing the process 2 to 3. So, cube 2 to 3 will be equal to, this is equal to 0, this is exit. So, this is H 3. So, H 3 minus H 2. So, this is very important equation, try to understand. So, we have discarded the changes in kinetic and potential energy, that means we have ignored V square minus V I square by 2 and we have also ignored G into Z d minus Z I, ignoring the changes of these two energies, and also we have noted that the control volume is not doing any work. So, this is the work only due to the flow process, and as a result of which this work we are getting enthalpy, not the internal energy. Had we have had the case would have had the case been first law applied to the control mass system, then instead of H we would have written U, that is the internal energy. But since the flow work is there, the work required to maintain the flow in presence of pressure, so that flow work component has now added with the internal energy U, and U plus that flow work, that is nothing but the enthalpy. But we have ignored the changes in kinetic and potential energies, and since this is not the work interacting device, so the control volume is not doing any work. So, only you are having Q. So, this is the expression. Now, what about process 3 to 4? Again changes in kinetic energy and potential energy are negligible. We are not telling that the kinetic energy is neglected, but we are telling changes in kinetic and potential energies are neglected. So, we are not telling that at the inlet of the turbine we are having velocity, we are having kinetic energy of the steam entering to the turbine. We are also considering kinetic energy of the steam leaving the turbine, but we are ignoring the changes in kinetic energy across the turbine, changes in kinetic energy of the steam across the turbine. So, the steam while flowing through the turbine, we are having a process, it does work on the moving component of the turbine, but during expansion we are ignoring the changes in kinetic and potential energies. So, if I apply this, what we can write? So, you can see this is there is no heat interaction. If we consider the control volume, so there is no heat loss. So, the reversible adiabatic process, so Q will be equal to 0. So, there is no heat interaction, rather we are getting work output. So, turbine is a work interacting device, not heat interacting device. So, if that is the case, this component will be equal to 0. So, H I, that is H 3 plus these two components, the changes of these components will be equal to 0. So, we can write H 3 equal to W 324 plus H 4. So, we can write W 324 equal to H 3 minus H 4. So, this is the equation, right. So, we have identified these two processes, we are having another two processes. So, that is the condensation process 4 to 1. So, process 4 to 1 I am writing again changes in kinetic and potential energy are negligible, right. Here we are having no work interaction, control volume does not perform any work, right, but we are having heat rejection. So, if we apply this equation, this component will be there, W will be equal to 0. So, this is H 3, this is H 4, right. So, I mean, so no let me, so this is 4 to 1, inlet is 4, outlet is 1. So, this is inlet H 4, this is H 1. So, we can write cube 4 to 1 equal to plus H 4 plus H 4 I am doing this, I could have written straight away the final form, but I am doing this only to make you understand. H4 equal to 0 equal to H1. So, you can understand cube 4 to 1 equal to H1 minus H4, or we can write minus H4 minus H1. You will be getting the direct expression, that is 4 Q1 like this from different texts. So, the minus sign indicates that is heat is getting rejected from the system. Enthalpy at point 4 is higher than the enthalpy at point 1, but the negative sign is an indication of having heat rejection from the system. Finally, you are left with one process, that is process 1 to 2, right, process 1 to 2, that is pumping process. Again I am writing changes in kinetic energy and potential energy are negligible. Okay. So, then so you can understand again, pump is there is no heat interaction, reversible adiabatic process, internally reversible, but there is no heat interaction. Then it will be, if I apply this equation, that is first law applied to flow processes, steady state steady flow. So, the first term will be equal to 0, here inlet is 1. So, H1 equal to W1 to 2 plus H2, sorry H2. So, 1 W to 2 equal to H1 minus H2. See, I mean here I will discuss about something which is very important. So, work done in a reversible adiabatic process. So, this is the expression, work done in a reversible adiabatic process. This will, it is not PdV work, try to understand, this is not PdV work, rather this is VdP work. By how we are getting work done in reversible adiabatic process, if we apply second law of thermodynamics. So, ds equal to del cube by T, reversible adiabatic process, no heat interaction. So, this is equal to 0, this fellow equal to 0, right. So, if I integrate it from process 1 to 2, so S2 minus S1 equal to 0, I am writing the specific quantities. Okay. Now, what I can write, the property relation TdS is equal to dH minus VdP, this is called second TdS equation. Again I am not going to discuss because you have studied in thermodynamics. This quantity is 0, so dH equal to VdP, right. If I integrate from process 1 to 2, from 1 to 2, we are getting H2 minus H1 equal to 1 to 2 VdP. What is here? So, we can write this is minus H2 H1, we can write this is minus 1 to 2 VdP. So, work done in a reversible adiabatic process is nothing but VdP work, only to make you understand that this work is not PdV work. So, this work is VdP. Had it been PdV work, it would have been 0, because PdV is basically pressure is remaining constant, but in pump there is a change in pressure. So, and also had it been PdV work, there is no change in specific volume of the liquid which is being handled by the pump. Pump handles incompressible liquid. So, basically there is no change in volume, specific volume of the liquid. So, had it been PdV work, the work done would have been 0, but this is not the case here. So, this is minus VdP. We have established that from where this work is coming. For your information, whether it is reversible adiabatic or reversible isothermal process, the work done associated with reversible adiabatic or reversible isothermal process is always VdP work, and that we have derived. So, the work associated with reversible adiabatic process is VdV, provided if we ignore the changes in kinetic and potential energies. Okay. So, there is one important assumption is that we are going to ignore the changes in kinetic and potential energy. That is why the work done for any reversible adiabatic process can be written minus VdP. As I told you, for your information, work done in a reversible isothermal process also can be written in the same form, provided the changes in kinetic and potential energies are considered to be negligible. Okay. To summarize, we have tried to understand that if we try to eliminate the problem which we have seen in the ideal Carnot cycle, the ideal Rankine cycle is better. The problem associated with those with the ideal Carnot cycle are not there in the ideal Rankine cycle, but still there are a few issues. Because of those, the efficiency of the ideal Rankine cycle is always less than the ideal Carnot cycle, but as we have discussed that our objective should be to bring the efficiency of the actual cycle closer to the ideal Carnot cycle. For that, we also need to find out several modifications. Before that, we also need to understand that why the efficiency of the ideal Rankine cycle is lesser than the ideal Carnot cycle. For that, we have also discussed about the mean temperature concept. Mathematically, we will try to show from the perspective of the role of the mean temperature while defining the efficiency of the vapor power cycle, that because of the reduction of the mean temperature, which is essentially due to the sensible heat component present in this particular ideal Rankine cycle, we are getting slightly less efficiency. Finally, we will try to discuss about the, though we have called it ideal Rankine cycle, but still we need to discuss about the presence of irreversibilities. Though the processes are internally reversible, but we need to identify whether the external irreversibilities are there or not. So, those aspects we shall discuss in the next class. Thank you.